First of all, I would like to thank Professor Eric Orel and Professor Bo Wahlberg for giving me this honorable opportunity to present our recent work on complex sensing. Okay, this is the outline of my talk. Actually, the complex sensing is a very fashionable topic in information science, okay, information theory and signal processing, etc., etc. And there was a big bang about 5 years ago, and actually we have two established very famous theories for analyzing it. So actually my talk is intended to build up a new theory. So as a theoretical background, after I define the problem that I want to focus on, I will shortly review two established the theories about that. And after that, I will mention what is insufficient or unsatisfactory for me. And I will build up a new method to analyze performance of computer sensing based on the technique of statistical mechanics. And I will show our advantage by showing some analysis of two example problems. And we end up this talk with a summary. Okay? Okay, let's start with a very simple question. The possibility of perfect reconstruction of n-dimensional x, vector x, real vector x, from its linear transformation, fx. We make it, call it y. Okay? For simplicity, we will not consider either rank deficiency nor noises. Then answer is very simple. Okay? If the matrix itself is vertically long, then it has enough sufficient number of conditions to determine x. So reconstruction is possible. Okay? But if the matrix itself is horizontally long, okay, then the problem is underdetermined, so we cannot uniquely determine the solution. So impossible. This is just a consequence of linear algebra. Okay, very simple problem. Next, let's consider this case, reconstructing sparse vector. Okay, let's consider the case of a horizontally long, okay, horizontally long matrix. This case, in general, impossible to reconstruct x. But even if the number of measurement, I will say that this dimension number of measurement, p is smaller than n, the reconstruction becomes possible if x is S-sparse. S-sparse means x is guaranteed to have the non-zero element up to at most S non-zero element. Other one is 0. So if such property is guaranteed and the position of the non-zero elements are known, then such a horizontally long case is reduced to the vertically long case. Okay? By arranging the vectors positions, the elements positions, we practically have this type of smaller matrix, and we can solve this by a usual treatment, right? So even if p is less than n, so even if fewer measurements, if we have a knowledge of the position of the zero element, we can solve this problem. Okay, this is still simple. And interesting question comes out. This case, it is similar to the previous one, but one point is different. Okay, how about the possibility of if x is guaranteed to be S-sparse? So non-zero element is guaranteed to be at most the number is S. So most zero element often. But positions of non-zero elements are unknown, right? Okay, this is a bit non-trivial. Okay, so before giving an answer to this question, I want to mention the significance of this problem in practice. Okay, actually, this type of problem is related to various technologies of modern signal processing. I borrowed one example from the medical engineering, computed tomography. Okay? This is used to investigate the inside of our body, so brain. Okay? One simple way to investigate our inside of our body is cut the head. But it is very dangerous. I don't like to do that. So we use this type of technologies using X-ray. Okay? In these devices, we project X-ray from the many directions. Okay? Then we can get some partial data of two-dimensional Fourier transformation. Okay? And Fourier transformation is basically the linear transformation. So the measurement can be expressed as y equal fx. X is the original image. Okay? And once having the data of Fourier transformation, by applying inverse transformation, we can get distracted image, so recovery. Okay, fine. Okay? And for the diagnosis, we want to have a high resolution. But there is one problem. Okay? To get a good resolution, we have to have many data, right? But this means that this increases the X-ray exposure. But at the same time, this increases the risk of cancer, damage of the tissues. So there is a high demand for imaging, for the image reconstruction from fewer data, okay? Fewer number of data, to reduce X-ray, to reduce the risk of X-ray exposure. So mathematically, this is nothing but the situation of this type, right? Very simplified situation becomes like that, right? So it is very important problem in practice. Then what is the answer? Okay, what is the answer? What is the best strategy to retrieve the sparse vector when the position is unknown? The answer is the following: the exhaustive search. Okay. So let's try all the n choose p. Okay, the reconstruction is possible, becomes possible by exhaustive search method if the S is the upper bound of the non-zero element of the original image is less than the p minus 1. P is the number of measurement, right? Then we can show that reconstruction is possible. Why? This is the reason. The following. So try all the n choose p minus 1 possibilities of non-zero elements, all the positions of non-zero elements, under constraint of the p minus 1 non-zeros. Then we can say that correct solution satisfied this equation because this the measurement was produced by the correct solution. Okay, this is one statement, but none of the other p minus 1 sparse possibilities can satisfy all the p constraint because the shortage of the degrees of freedom. Okay, we now have the only the p minus 1 elements are non-zero, but this equation have a p constraint. Then the degrees of freedom is shorter than the constraint. Then nothing. There are no solution. So this means that the correct solution can be characterized by some vector among that have a probability that minimizes the number of non-zero elements. From now on, we call it L0 norm that minimize L0 norm among the vectors that satisfies this measurement constraint. Okay? So by solving this constraint optimization problem, we can recover the original signal. If the sparsity parameter S is smaller than the number of measurements. Okay? Okay, this is a great approach. Okay? But unfortunately, this approach is computationally difficult to perform because it is basically the exhaustive search. So the cost of computation increases exponentially with the size of the problem. So as a practical feasible solution to this difficulty, reconstruction based on the LP relaxation is widely studied. LP relaxation is defined like modifying the cost function to the LP norm, LP cost. This is defined as this one. So the summation of the absolute value of the entries powered by P, right? So this becomes, okay, L0 norm is a discrete numbers, but this becomes a continuous one. So we can apply a lot of techniques to the optimum. So local search is possible, something. And also, in particular, if the P is greater than 1, or equal to 1, we can guarantee the cost function is convex. Okay? So much more preferable. So, so in particular, so much attention has been paid for the L1 reconstruction because it is performable in polynomial time by linear programming methods and a high capability of the sparse reconstruction. This is confirmed by empirical way. And actually, there is one famous benchmark in the problem of the computed tomography. Okay, they did some simulation. This is actually the artificial data. This is the Logan's phantom. It's very famous, the picture. And also, this is a sample of the pictures. They did some experiments that they did some measurement of the 12 samples along the 22 different directions. Okay, then we can get some fewer data of the two-dimensional Fourier transformation. Okay, this is the original signal, and the conventional method is using a pseudo-inverse. Okay, now the problem is defined by the rectangular matrix. So one traditional strategy is to use the pseudo-inverse, right? But using this, you can have this type of, you can detect, you can find this kind of shapes. But at the same time, it has some noises here, right? Okay. It is unsatisfactory. But using a kind of the L1 reconstruction, so minimizing problem and the constraint of the measurement, actually in this artificial case, there are no errors. So perfect reconstruction for the both of the two examples. Okay, very impressive the result, experimental result. So it is kind of yes. It created some big bang. So after that, much effort has been paid for clarifying the capabilities and limitations of the LP reconstruction, in particular L1 reconstruction, right? Okay, so far I just mentioned about the cost function, but there is also some important properties in this system, matrix S, how a matrix is chosen. And so far, there has been also been a major interest in random measurement matrix F. And today, I also focus on this random matrix. There are two major reasons. The first one is that to theoretically handle this type of problem, it is a bit annoying to consider the specific properties of the systems in the objective system. So avoiding the specific individuality, so they assumed the random, some ensemble of matrix. This is one reason. And another reason is that I don't mention details, but the Candes and Lomberg showed that typical sample of random matrix guarantees very good performance. So it is said by the incoherent sampling. So actually random measurement itself is guaranteed to be very useful. So there has been a major interest in random matrix in this field, right? And for this setting, so L1 reconstruction and random matrix, there have been two key theoretical studies. Actually, from the 5 years ago. So I'll shortly explain these two from now on. Okay, the first one, yes, invented by the Candes and Tao. Okay, the idea of them is that look for a condition under which this underdetermined system has a unique solution when X is sparse. Okay, this is the idea of their strategy. To consider this problem, let's consider why undersampled signals cannot be recovered generally. It is very easy. Okay, this is the correct solution. But if the F is horizontally long, it always has null space. Null space means the set of vectors which satisfy this equation, Fz equals 0. Okay? Then if you have a null state, you can add this z here. And this is not the 0 element, right? This means that we have at least two equations, actually many equations. So we cannot choose unique solution. This is the reason, right? In general. But in our setting, we have extra condition, an extra condition. We, under the assumption, in our assumption, X is guaranteed to be S-sparse. So for these two expressions must be S-sparse under our setting. So then the Z is a difference between the two vectors. So let's consider the Z, property of Z. Then this is one solution, but this is S-sparse, and this solution S-sparse. Then the mismatch, the number of mismatches is at most 2s. Okay, it is guaranteed. So for the null space, we can impose an extra constraint. So the vector must be a 2s sparse, right? Then if the following, this statement holds due to this extra condition, we can guarantee unique recovery because Fz equals 0 means Z equals 0. This means nothing but the uniqueness of the solution of y equals fx, right? Okay, this is the idea. And the following notion is very useful to implement this idea in mathematics. Restricted isometric property, RIP. This is a definition of the RIP. Okay? If this inequality holds for any S-sparse vector x, the matrix F is said to satisfy the S-restricted isometric property RIP with the RIP constant delta S. Okay, very complicated. Okay, but if using this constant, we can express the condition of the uniqueness in a very complicated, very simple manner, right? Actually, if the delta 2s, the RRP constant is smaller than 1, we can directly say the solution is unique. Because if this constant is smaller than 1, we can guarantee that this constant becomes positive. Okay, 2s case. Okay, 2s case. 1 minus delta 2s is positive. Then this means if fx equals 0, then positive number multiplied by the 2 norm is bounded by, upper bounded by 0. So this means x equals 0. Okay? So this means, so we can say this for the 2s space vector z, fz equals 0 means z equals 0. So this means the null space is empty, practically empty. So the solution is unique. Okay, very complicated, very compact manner. And the second line, this is very important, but I don't mention detail, but it can be shown that the solution of the L1 reconstruction accords with this correct solution. Also, if the RRP constant is smaller than square root 2 minus 1. Okay? This is the key point of their theory. But what I want to say is that such conclusion can be expressed in a simple manner using the concept of RIP. Right? So this is the key concept. Okay, this is great. But again, unfortunately, evaluation of the RIP constant for a given specific matrix is generally difficult. So in general, it is difficult to go further. But one can still statistically evaluate it for ensembles of matrices using a theory of random matrices. Okay? And actually, for several types of random matrices, it has been shown that this statement holds statistically with a high probability if this condition is satisfied, as all parameters p and n and s go to large. And this provides a sufficient condition under which L1 recovery typically succeeds in a perfect reconstruction. Okay? This is the outline of the Candice-Tau theory. Right. Okay, comments on the Candice-Tau theory. Okay, it is great. Okay? What is the advantage? Advantage is, firstly, mathematically rigorous. Okay? And also, it has a nice property that wide applicability. Actually, this is applied for the very simple setting, basic setting, but it's also applicable to some kind of matrix completion problem. Matrix completion problem is that we have some partial portion. The partial portion of the matrix entries are given. And the problem is how to interpret other entries. Okay? This is a kind of the matrix version of the complex sensing. Okay? To analyze such concept of the RIP is also applicable. And also even analysis of the other heuristic method, this concept of RIP is very useful. Okay, very fine. But there's still one drawback, at least. Unfortunately, the assessment is generally not tight. Okay? We can get some sufficient condition by expression in equality. But we can also do some computer simulation. Then the obtained bound by the RIP theory is generally far from a threshold suggested by experimental observations. So there seems much room for the improvement. Okay? This is, I think, the one possible drawback. Okay? Then let us move to the second one. Second major theory for the complex sensing, invented by the Donohue and Turner. Okay? Their idea is completely different from the one of the Candace and Tao. The idea is follows a geometrical argument on linear programming or convex programming. Okay? Let us consider the very simple case of the complex sensing. Okay? We assume that the original vector is two-dimensional, only two entries, and just one measurement. And we guarantee the correct vector is S-sparse. So only one entry is non-zero. Okay? In such case, we can draw a figure, right? This is the figure. Okay. This blue straight line indicates the measurement. Okay? In a product, defines a line. And this square means contours of L1 node. Okay? So giving some value, we can draw some contour. And the cross point of this measurement line is a feasible solution. Okay, and this means that as the value becomes larger, the size of the square becomes larger. Okay? And as the value becomes smaller, this shrinks. And this situation means that we still reduce the number, the value of the L1 cost. So we shrink. Okay? Still we can shrink the size. Shrink. Then we can get the correct solution, indicated by red spot. Okay? This is the reason why we can get the correct solution by L1 minimization under constraint. Okay? But actually, this is not always the case. Okay? This case, failure. Because this is the correct solution, but the slope of the measurement line is steep. So it is touched this corner, the wrong corner. So in such case, the L1 deconstruction fails. So it becomes so which occurs determined by in a manner of probability. And actually, the success probability is defined by a geometrical argument by this angle. If the slope of the line falls in this region, the L1 reconstruction is successful. Otherwise, failure. So this means that the probability of success is 1/2 in this case, right? So considering the some geometries, volumes, we can estimate the success probability. Okay? Actually, surprisingly, this is very simple in the two-dimensional case, but three-dimensional case already non-trivial. Four-dimensional, five-dimensional, non-trivial. But surprisingly, the Donohue and Turner managed to do it in general dimension, right? And the probability of success can also be evaluated in high-dimensional cases in similar, so counting numbers, so combinatorics, right? And the problem is finally reduced to the problem of counting the number of S-dimensional faces for P-dimensional random projections of N-dimensional polytopes. Complicated, right? But it is possible. And they gave us some formula like that, probability of success, like this. And when you take this type of limit, so PNS, the large system limit, keeping ratio of the measurements over the number of original dimensions and the number of the density of the element of the one, then we can get this type of behavior about the probability of success probability. Okay. this horizontal axis means that the ratio of the measurement over the against the original dimension. So that this is a kind of number of the measurement. So if the number of measurement is sufficiently large enough, then the probability success converges to 1. So typically successful. But if the number of measurement is not insufficient, then the probability of success converges to 0. And there is some threshold, or critical threshold, alpha c, which depends on the non-zero density rho, right? And using this formula, exact formula, they evaluated the accurate value of alpha c rho in large system limit. Yes, it's a very elegant work. So comments on the Donohue-Tanner's method. Advantage is what? Mathematically rigorous. Okay, fine, very good. And also, we can say that accuracy is a good point of this method. The threshold is extremely, excellently in accordance with experimental behavior. So you can do a simulation. And you can evaluate experimentally the probability of success. Then you can check this behavior very in accordance with the theoretical prediction and the experiment, right? So very good theory. But I think there is at least one drawback still. What is applicability? Unfortunately, even if you change the setting slightly, such counting method is difficult to apply, right? So maybe in practice, the range of application is a bit limited. So I think this is drawback, right? So this is a short review of the earlier works. Now I want to explain our standpoint. Okay? Both of the two earlier methods mathematically rigorous, but both has one drawback at least. The Countess-Tau method not so accurate, and the Donohue-Tanner's method is technically difficult to apply the complicated setting. So we want to cover these drawbacks. Okay, these drawbacks. So our purpose is for handling more advanced setting. Okay, the problem shown here was a bit too simplified. So I want to tackle with a bit more generalized setting. So to do so, we want to develop another systematic method to for accurately evaluate the thresholding value of alpha c rho. Okay, this is my object. Okay. So our analysis. Okay. The first I explain for the basic setting because to compare the previous methodologies. Okay. The idea is a bit different from the two previous ones. Okay. Our idea is to follow the Bayesian framework. Okay. So assumptions. We assume that the x0, the correct vector is S sparse. To express such assumption in Bayesian framework, we introduce the correct prior for the data generation like that. So this becomes the entry becomes non-zero with low with some probability. This is unknown, but we guarantee that it has unit variance. Yes, and also I assume that zero mean unit variance. Okay, but details anything is okay. And with the probability 1 minus low, this becomes 0. So sparse prior. And for the measurement matrix, we assume the Gaussian IID, lambda, the same as the two theories. And also consider the large system because I want to employ the statistical mechanical method, so this situation is considered. Okay, it is assumption for the data generation. But what we have to do is inference from the data. So this is assumption for this stage. To do some LP reconstruction, we formally consider some prior this form, right? This is LP prior, which I say, right? And in addition, we have some measurement, y equal fx, okay, is given. So combining the two, Bayesian framework provides us with posterior distribution. Okay, this is just a direct application of the Bayesian framework. Okay, then using this, we can infer the original vector. This is the very standard strategy to infer something. Okay, just follow the Bayesian framework. And actually, the LP reconstruction, so minimizing something under the constraint of the measurement, correspond to the LP, that correspond to the map estimation for these posterior probabilities. Okay? Because the delta function, this means that this requires the hard constraint for the solution. So this is the constraint like an optimization problem, right? And map solution according to the posterior mean of the beta infinity limit, right? Beta, we consider this kind of parameterization. And if you take the beta infinity limit, just minimum the state of the LP cost is chosen under the constraint of this one. Okay. Then to measure the quality of the solution, we introduce the mean square error per element, right? The L2 norm of the difference of the true and estimated one. Okay, this one. And this bracket means the average of the posterior distribution. Okay, this bracket means the average of the posterior average. Okay, but this still depends on the each individual realization, not x0 and f. Okay, so we have to further average over such realization of the true vector and measurement matrix. So we have to perform some nested average calculation to evaluate the typical mean square error. This is the point, actually. By the way, we can expand this term by using some formula, okay, just a square formula. We decompose the term, this is three terms. That Q is basically the square norm, and this is overlapped with the true one and recovered signals. Okay, then we can say that if the epsilon equals 0, there is no errors, okay, between the true and estimated one. So success reconstruction. And if epsilon is not 0, this means there is some deviation. So recovery is failure. So we can say that using this criterion, we can yes, characterize in each parameter, the reconstruction becomes successful typically or not, right? Okay, this is the strategy. But there is one technical difficulty. Actually, such nested average, this is the point. Such nested averages are difficult to evaluate in general. Okay, to explain this, I write down straightforward manner like this. And the source of the difficulty comes out here. Okay? To evaluate the posterior average, we have to compute this stuff. But for this, there are some of the something. Okay, this factor comes out in the denominator. This is the point. So due to the existence of this denominator, this calculation becomes very hard. Okay? Just straightforward calculation, maybe do that. We can do that. But it requires a lot of computation. So very computationally hard problem. Okay? This is so we want to get rid of this difficulty. Okay? So what should we do? The one solution is to cancel the denominator by multiplying the nth power of the z. Okay, zn. Okay, this zn is the sum of this is the denominator. Okay, this is nothing but this quantity appears in the denominator. This one, the part by n. Okay. Then using the expression, the expansion, we can get this formula, and finally this becomes like this. Okay, and we call these n bracket terms, right? These summations, this variable, as replicas, because these are regarded as some n copies, the shares, the same randomness, f and x0. So this is the origin of the name of the method, replica method. Okay. Then multiplying this to this stuff. Okay. In the denominator, this is z. So we can cancel 2. And this already also still remains n minus 1 power. So on expanding this one using this form, we finally get this expression. But you can see that there is no denominator. So this, some technical difficulty seemingly disappears. Okay. This is a key idea. So having this observation, we consider this type of trick. Okay. First, we define some modified average of Qn. To what the goal is of this one, to obtain this one. But without directly evaluating this one, we consider this modified one, which have the n here. Okay? But the n, due to the argument of the previous slide, there is no denominators. So actually this is feasible to evaluate. Okay? Then we consider the following. So analytically assess the expression Qn as a function of n. N equals 1, 2, 3, 4. Okay? Utilize the identity of this one. Because this one does not have denominator, we can do analytical evaluation for given any n equals 1, 2, 3, 4 natural numbers. Okay? Then we assess a nested average here via the formula of B, this one. This is the exact formula. Because z is a positive number, z to 0 is always 1. So taking N0 limit, this disappears and nested average is computed. Okay? But we just evaluated the Qn just for the integer point. So in principle, it is impossible to do the n to 0 limit. But we assume that we can do an analytical continuation as a function of n for Qn. So assumption, we introduce assumption. So by employing the analytical continuation, of the Qn to n, from the natural number n to real n, and take n as the limit. Then we finally get this nested average. This is the main backbone of the replica method. Okay? And in practice, the assessment is reduced to the saddle point evaluation of the moment of the partition function z. So the nth average. And with respect to the macroscopic variables QAB, like this, and MA. And for this, actually, in general, we have several candidates of the saddle point in the evaluation. Okay, because this is a multivariate analysis. So there can be many varieties. So to do this, we have to select the dominant one. So the guidelines are following, replica symmetry ansatz. So let's see that this the expression. So this expression means that this computation, every replica is equivalent, right? This means that the dominant saddle point is likely to also have this property. So it does not, it should not have a dependence on AB replica indices. So assuming this, that we have some saddle point problem to determine the value of the nested average, Q and N. Okay? And this is such problem. Okay? So solving this extremization problem, we can determine the value of the Q and the nested averages. And actually, we solved the saddle point problems this type, p equals 0 and 1 and 2 case. And for all cases, only the successful solution of q equal m equal rho. Actually, epsilon equal q minus 2m plus rho. So q equal m equal rho means epsilon equals 0, so successful. Solution was found when alpha is sufficiently large for a fixed signal density rho. And the reconstruction limit alpha c is determined by the local stability condition of the successful solution. So we can determine the value of alpha c by following our methodology. So this is the result. And actually, the p equal 1, the p equal 0, and the p equal 2 case, it is trivial. Without using replica method, you can get this solution. Okay. But the non-trivial case is 1 result. And actually, it is gains by solving some nonlinear equation to express a stability condition. And surprisingly, not surprising, but actually this completely accord with the result of the Donovan Turner. They did some calculation by the combinatorics. And the two methodology becomes identical. The result identical. Okay, fine. And we to confirm it experimentally, we did also some numerical experiment. And we did some large experiment, 10 to 6 times experiment for the n equal 10 to 30s. But for the finite size effect, these points are different from the theoretical prediction, but extrapolated value is very close up to the 3rd digit. Okay? So maybe it confirms the validity of our methodologies. Okay? So our methodology reproduced a non-rigorous result by Donovan Turner for the basic settings. Fine. Okay? So the justification of our non-rigorous approach, but the result is the same as the rigorous, the one of the rigorous method. But only this is not sufficient for showing the significance of our approach. Okay, just a reproduction. So no need to push this theory. So, but for what I want to do to push this theory, so I want to show one advantage that the methodology can also be employed to analyze more advanced, a complicated setting. So this is our advantage. So I will close up my the talk by showing just 2 simple examples. Okay. The first one is a site-dependent prior. Okay, and this is one example. Okay, this is by Tanaka and Raymond, and their observation is following. Prior of the sparseness can be site-dependent. Actually, this is a nice right image of Japan. Okay, Japan has a lot of industry around here. This belt area, and this area is countryside. In the night, there is a very the dark places. Okay, so the darkness and lightness depends on the site. The industrial site, the density is high, and the countryside low. Okay, such things can occur in the practice situations. So the motivation is how much can be gained by improving so employing such prior information in the complex sensing scenario. So they did some calculation for a very simple toy model, 2 block models. Okay, this is the same setting, but they assume that first half entries has a large density of non-zero, and the latter half is a smaller density of non-zero. Okay, this is considered as a usage of the prior knowledge. Okay, and they also introduce some adjusted parameter for the L1 norm, depending on this difference of the prior probabilities. Okay, and in such system, it is very difficult to apply combinatorics. Okay. Only such modification, the combinatorics become very complicated, very hard. But we can do that by the replica method, and they show that the gain is accurately evaluated by the replica method. These lines, these difference lines correspond to the weight parameter adjustation, right? And this cross means experimental results, and this is in accordance with the theoretical prediction very well. So very good. This is one example. And another example of the awards, influence of the non-orthogonal basis. Okay, so far we assume that we can measure the sparse expression directly, right? But in practice situations, such situation is very rare case. The instrumental constraints can make it difficult to measure the sparse expression directly. For example, the sensor network. Okay, this example is from the Haupt et al. 2008. This is a monitoring of the physical field, maybe temperature, window, something, humidity by a network sensors, low capability sensors. Okay, the field could be expressed as a sparse information in a certain domain, maybe Fourier domain or wavelet domain. If you choose appropriate basis, this could be a sparse. But direct measurement is in such domains difficult, technically difficult by this kind of sensor networks, because the capability of sensor, so each sensor is limited. So applying some Fourier transformation in this group of the sensors is impossible. So that what one can do is just directly observe something and multiply some weight and parse the information. Such low-level calculation is possible, but the other advanced one is impossible, usual situation. So in such cases, the setting should be modified slightly. Okay? So random measurements should be taken for the dense signal in general, right? And the dense signal may be expressed by a sparse vector using some appropriate basis, B. Okay? And after having the measurement, we have to solve this equation for having a sparse expression like this. Okay? Seemingly very similar to the previous setting, but the one property is different. Okay? In the previous situation, F is completely random matrix, but we have now a B here. So this could create some non-trivial correlations among entries. So it might be change the performance significantly. Okay. So our purpose is how significant is the performance influenced by this difference of the setting. But we can get a partial answer by some slight, very short consideration. If B is an orthogonal basis, actually the performance of the random measurement is the same as the basic setting. Why? This is because if the F is a random matrix, we can apply the singular value decomposition like this form. Then we can say that this left eigenbasis and right eigenbasis is a sample of orthogonal matrices. Uniform, typical sample of uniform distribution with a random orthogonal matrix. Okay. Then what is the recovery matrix? A recovery matrix becomes like this, but using this formula, okay, we can find this form here. It's orthogonal matrix. But if B is orthogonal, B transpose V also orthogonal. And if this is a random one, random sample from the uniform distribution of the orthogonal ensemble, this also has the same property. So this means that we can regard this recovery matrix as another typical sample of the random matrix. So fine. So this is very good news in practice, because this is highly preferable in practical situation because various signals in nature are empirically known to be sparse in a certain Fourier wavelength, namely the orthogonal domain. So we can enjoy the same performance in the as a theory. But still, this does not cover all cases. So our motivation is what happens if the basis is not orthogonal. This is the point. So as a simple case study, we consider this model. So sparse variation 1D signal. This is a kind of time series, but it basically follows the AR1, autoregressive 1, but often it stays the same state, right? So the signal itself looks like that, signals. But this signal is not dense, the sparse. This is dense signals. But if you move to the difference of the time series, this is sparse. Something. So we calculated the case that this is measured by the random sensing, random measurement, and applied the L1 reconstruction using this basis, right? And actually the result is this one, and you can see that it is very similar to that of the basic setting, right? Actually this becomes worse, the performance becomes worse. But at the same time, we can say that the loss is relatively small. Actually this result encourages use of CS for a wider class of applications that one cannot expect the orthogonality of the basis, okay? So this is the end of my talk. Okay, so summary. Okay, we have developed some unified methodologies. So the systematic methodologies for analyzing the performance of computer sensing based on the replica method of statistical mechanics. Okay, this is my main message. And compared with the two earlier very famous methods, maybe the status of a replica based scheme is summarized as follows: this table. Okay, the two famous methodologies, okay, they are the mathematically rigorous. So mathematical validity is excellent. But our drawback is that here, cross, okay, no mathematical validities, okay. But still has the advantage, two advantages. First is accuracy, okay, the alpha C is very accurate. Compared to the experimental result. Also, we have some very flexibility, so we can apply the same methodology to the wider variety of the model settings. Okay. How much time? 1 minute. Okay. Okay. This is related to studies. So that's all. Okay. Thank you for your attention.